This is VLSI data conversion circuits, lecture 43. In the last class we were discussing various mechanisms by which the latch can give a wrong decision. Of course, systematic problems are ones like hysteresis, which we have learned to fix using a reset phase phi 3. Towards the end of last class we saw that random mismatch between transistors can also cause errors in the decision, because static mismatch in the transistors which form the main regenerative pair, as well as mismatches in the switches and the parasitic capacitances at x and y equivalently appear as if you are not comparing Vx and Vy, but some Vx minus some delta V1 and Vy minus delta V2. So, it is an error in the threshold of the latch. Another important mechanism is what is called dynamic offset, and the mechanism that causes it is as follows. So, this is our standard latch we have been discussing so far, and just at the end of phi 1, right, if the voltages on capacitors Cp1 and Cp2 at x and y were slightly different, right. For example, let us say this is Vcm 1 minus delta V and this is Vcm 1 plus delta V, okay. And let us say the inverters have a natural trip point. And what do we mean by the natural trip point of the inverter? It is that input voltage at which for which the NMOS and the PMOS currents are the same, right. Let us say the natural trip point of this inverter is Vcm, which is not equal to Vcm 1, okay. Now, what do you think will happen in the very beginning? So, at the end of phi 1, these inverters circled in green are not yet turned on. So, the initial conditions on Cp1 and Cp2 are Vcm minus delta V and Vcm plus delta V. The moment the inverters turn on, what do you think happens? If Vcm 1 was exactly equal to the trip point Vcm, what happens? The currents that each inverter would pump would be, I mean, Gm times delta V and Gm times delta V in the right directions, right. Now, what happens? If you apply, I mean, let us think about it carefully. The initial voltage at this node, as soon as the inverters are turned on, is basically Vcm 1 plus delta V, but the trip point of this inverter is Vcm. So, to a first degree, what is the current that is being supplied or pushed out by this inverter? It is Vc m1 plus delta V minus Vcm times some transconductance Gm of the inverter. Is this clear? Similarly, this let us call this going this way, this current then will be Vcm 1 minus delta V minus Vcm times Gm. Okay. So, for small delta V, which is what is of serious concern for us, because the latch is most likely to make an error when the two inputs are very close to each other. So, what is the big departure from the previous situation? If Vcm1 was exactly the same as Vcm, then if one inverter is pushing current in this direction, the other one is pushing current in the other direction. Whereas now, in other words, the current outputs of the two inverters was purely differential, correct. However, if the trip points of the inverter are different from the two initial voltages to which Cp1 and Cp2 have been charged, what do we see? There is indeed a difference in the currents which is still equal to 2 Gm into delta V. However, there is also a common mode component, okay. And what is that common mode component trying to do? It is trying to bring Vcm1 towards Vcm. And how do you see that? To determine how this common mode potential is moving, what do? We draw the common mode equivalent circuit. And what is the common mode equivalent circuit?
Twice the inverter with inputs and outputs.
So, we need to short to find the common mode response. I mean, this common mode and all this only makes sense when things are linear, right. In the very beginning of the degeneration phase, we hope that things are still linear because the input is very small and we are just looking at around the time when the phase phi 2 goes high, right. So, as far as common mode signals are concerned, we see that the impedance at the common mode impedance at nodes x and y is a very small number, right. In other words, this back to back inverter chain is attempting to, of course, regenerate the difference, but also at the same time trying to bring the common mode to Vcm of the, which is the trip point of the inverters. Does it make sense? Okay. All right. And I mean, another way of seeing it is that you can see that the current flowing here has got a common mode component, right, which is proportional to the difference between Vcm and Vcm1 and is pulling it in a direction so as to bring both of them close to each other. Is this clear? So, if you plot the waveforms at x and y, these two were slightly different to begin with, and this is phi 2 or regeneration begins. What do you think will happen in the, what do you expect to happen to the common mode? this was, what is VCM? This is VCM 1. Let us say this on the other hand is VCM, which is the trip point of the inverter. What do you think will happen? The common mode will attempt to go from VCM 1 to VCM in a very, very short time, corresponding to the time constant, right, which again depends on the GM of the inverters, okay. And at the same time the differential mode regeneration is also attempting to happen. Is that clear? Now the common mode going, so what you would think would happen would be that this would attempt to do something like this. This on the other hand, node X would attempt to do something like this, right. This way you can see that the differential mode is increasing, the common mode is also moving towards VCM, okay. And beyond this the common mode does not change because it is close to the trip point of the inverter, and then regeneration takes over. I mean the regeneration becomes very strong and perhaps does something like this. Okay. Unfortunately, in practice what happens is that the two capacitors CP1 and CP2 are not only mismatched, they are also non-linear, okay. So it will turn out that during this time, if the input difference is sufficiently small, okay, what will happen is that by the time the common mode moves to the natural common mode of the inverters, which is VCM, okay, an interaction between mismatch and nonlinear capacitance at Vx and Vy will cause the upper voltage to go below the lower voltage, and then regeneration takes over. And you get an error. All right. So in one of your exercises, you will actually be asked to plot all these waveforms and see this for yourself. The mechanism actually is somewhat subtle and difficult to rigorously analyze, or it is possible to rigorously analyze mathematically, but you often end up with a messy morass of equations, right. But the key point is to understand that the problem is appearing because of the difference between VCM and VCM1. The natural threshold of the inverters and the common mode of the differential input voltages stored on Vx and Vy is what is responsible for this offset which is called dynamic offset. Okay. All these diagrams of course are grossly exaggerated and greatly simplified. When you actually look at real waveforms, there will be a whole bunch of glitches on all these waveforms corresponding to charge injection and all this stuff. Okay. And every time a clock changes through the overlap capacitance of the switch transistors, you will find that there will be a component of the clock getting onto all these waveforms. So, in order to understand this carefully, you need to take a very careful look at all the potentials, right, in that early part of phi 2, you understand. But as I said, I mean, more than analyzing this, it is sufficient to recognize that this is a problem and the solution is quite straightforward, as you can see. What is the solution? So, the best bet to minimizing dynamic offset by choosing VCM 1 equal to VCM. Okay. So, this should also tell you why it makes sense to short the two nodes x and y together during the reset phase phi 3 rather than connecting them up to a common potential, namely VDD, right. Connecting those regenerating nodes to VDD is something which is done in a fair number of latches, and latches like this will be prone to a lot of dynamic offset, simply because during the initial part of the regeneration phase, the common mode of those two nodes will have to come down from VDD all the way to VCM, okay, which will can cause the difference between nodes x and y to reverse sign, and then by the time the regeneration takes over and stuff, it is I mean, it is too late because the error has already been made. Is this clear? So, this is a good strategy to choose, and often simulations of dynamic offset are done using Monte Carlo type analysis, where you put in device and process mismatch and keep putting in signals which are straddling the threshold, right. If you put too large an input difference, the output decision will indeed be correct. All these problems will only happen when the input is very small, and that therefore, you need to run a whole bunch of simulations where you randomly vary the thresholds as well as the parasitic sizes to get a good estimate of what this random mismatch due to whatever dynamic offset due to random mismatch, which will include both effects of nonlinearity of the capacitances as well as mismatch between them, are taken into account. And so, typical numbers to go by are about 40 to 50 millivolts of dynamic offset, are rough estimates, okay. And as I said, Monte Carlo simulations are the best way to estimate the true dynamic offset, okay, or rather true offset, which will include contributions from both static as well as dynamic parts. Is this clear? Okay. Now the question is, what does one do if one has such a large dynamic offset, correct? Let us say you are trying to build a 6-bit flash ADC with a 1 volt peak to peak differential signal range. What is the LSB size? It is 1000 millivolts divided by 64, which is about 16 millivolts. So, if the offset of the latch itself is 40 to 50 millivolts, that is almost like 3 to 3.5 LSB of the converter that you are trying to build. So, in other words, the latch, while it gives you, if you have sufficient time, gives you a characteristic which looks like a signum function, alright. This is VDD, this is ground, this is V offset, and this is a random quantity, right, which consists of static and dynamic components. And this offset, as we can see from our discussion, can be much larger than the LSB of the converter that we are trying to build. Now, the question is, what do we do about this? How do you think we can fix this problem? Clearly, the latch as such has decision levels which are in error by too large an amount. So, what do you think you can do? Ideally, what do you want this signum to be? I mean, you want this transition to be at 0, or if there is a variation in this threshold, it must be centered around 0 and must be so small that the DNL and INL of the converter are not drastically affected. Okay. So, what do you think you can do to reduce the effect of offset? In other words, let us see, this is V in and this is V out, correct. This is the characteristic we have. What we want is something where this is much smaller. So, let us say we want this where this offset has now been reduced by a large factor A. So, what do you think you can do? Pardon? If you want to take this characteristic and move the strip point from V offset to V offset by A, what do you think you can do? Yes, the input should be
amplify the.
Yeah. So, in other words, what you should do is not use this latch as is. This thing has got some offset, correct. If you put an amplifier here with a gain A, then, and if this is V in, what happens? So, the actual input going into the latch is A times V in plus V offset. So, the latch is giving us sine of A times V in plus V offset, which is equivalent to sine of V in plus V offset by correct. So, this amplifier again I am just taking the liberty of drawing single ended diagrams, okay. But this is the latch offset. This is called the preamplifier. And ideally, what must be the gain of the preamplifier? I mean, ideally, you would like to be like it to be infinite, and thereby reduce the offset of the latch when referred to the input of the preamp to 0. In practice, of course, the preamp will have finite gain, and the effectiveness to which it reduces by which I mean the effective reduction in the latch offset will be only by this factor. Okay. Now, what do you think is the problem with adding a preamp? Right. So, it is not quite fair to assume that there is mismatch in the latch and there is no mismatch in the preamp. So, if devices are mismatched, they are mismatched everywhere, which means that it is very likely that the preamp, whose job is to take the input voltage and multiply it by a large factor, right, it does not just give you A times V in, it adds its own offset. So, now we have tried to solve the problem of the latch by adding a preamp. Now, it does not help if the preamp itself has got offset, you understand. So, in other words, while this is a schematic, a more for instance, this is the preamp, and let us say this goes to the latch with all its additional baggage, namely the switches phi 1, phi 2, phi 3 and all that stuff. So, we do not worry about that for the time being. Our job now is to try and figure out what to do with the offset of the preamp itself. In other words, the preamp has got an offset which is so the output voltage is actually A times V in minus V offset. Now, the question is, what do we do to fix this? Issue of preamp offset. and please note that this is your preamp. You can't say why don't you apply the input here, right. I mean, it seems like the most obvious solution, but the bottom line is that offset is not accessible. Okay. Now let us see what we can do. Just to make sure that there is no confusion, let me draw the offset also in black. Okay, so the accessible terminals are all drawn in red, and the unaccessible part is drawn in black. Okay, what can we think about? I mean, what ideas can we come up with which will enable us to either eliminate or reduce V offset? Pardon?
That whatever the offset is there, at opposite polarity we can put.
Well, yeah, there are you can think of it in several ways, but the basic idea seems to be like, if we know V offset, right, then instead of applying V in to the preamp, we will apply V in plus V offset to the preamp rather than V in. Isn't it? So now the question is, how do we know, or how do we get to know what V offset is? Any suggestions? In principle, what will we do? Let me rephrase, or let me draw this again. How will we know V offset? We have an amplifier with some offset in it. How will we figure it out? Okay, apply 0 input voltage. Okay, that's the first idea is to say, okay, this has got a large gain A. Why don't I apply V in equal to 0, and therefore the output voltage must be minus A times V offset, okay, and from this hopefully knowledge of A and knowledge of V offset, I mean from the knowledge of A we should be able to get V offset. What do you think is the problem with this? Well, okay, a secondary concern is what he points out, which is, okay, knowing A properly is not an easy task, especially when A is very large. What is the more serious problem? The more serious problem is that if A is very large, just imagine this triangle to be an op amp, for instance, right. You have seen that the output voltage of the op amp is always either going to be either ground or VDD, because the gain is so high that it will saturate the internal nodes of the amplifier. Okay. So apply V in is 0, measure V out, get V from which you get V offset is not a good idea, because amp will saturate. Right. I mean, think about this as, I have an op amp with an input preferred offset, and I want to find what that offset is. What will you do? So, from your basic op amp classes, you take the op amp and you put it in unity feedback, and what will be the output? This output will be, please check carefully, it is minus V offset, correct? Does it make sense? But then if you put the op amp in unity gain feedback, you have minus V offset developed at the output of the op amp. Okay, then what do you need to do? We need to store this quantity and subtract it from the input voltage source. So, how do you store an analog voltage on a capacitor? So, I would say, and please note that it is not good enough to simply connect this to ground always or to close this feedback loop always, because after we are done with estimating offset and hopefully fixing it, we want the amplifier to amplify with a large gain, correct? You understand? So, in other words, these lines drawn in red must only be active during that period during which we are estimating and storing the offset. Okay. So, in other words, let us call that let us call this phase phi A Z, the strange choice of clock name. AZ stands for auto 0, right, and is the trade name given to any technique which removes offset. Offset cancellation is also called auto zeroing. Okay, because in the old days when there was offset in the amplifier, you would have some kind of potentiometer control. You would look at the output and go and turn something, and the output would go to 0. This is called zeroing the output of the op amp of the amplifier, right. Now, this is all done automatically. So, presumably this you can call this auto 0. So, when phi Az goes high, the positive input terminal of the amplifier, the preamp, should be connected to ground, right. You should enable the unity gain feedback path around the amplifier phi Az, and what happens at the output of the amplifier? The voltage that is developed can be stored on a capacitor, right. So, where do you think you can put the capacitor? I mean, one way of doing this is to say I am going to have a capacitor here, correct, and what happens to this voltage now? What is the voltage at the end of phi Az? What is the output, what is the voltage across CAZ? Minus V offset, and then if you say during phi Az bar the input is applied, what will be the output voltage? V in minus V offset minus of minus V offset times A. All right. So, this gives A into V offset. Sorry, I am sorry, A into V in, yes. Okay. I mean, another alternate way of doing this is to say during I mean, it is not necessary, as you can see, to attach V in here. One can also where else do you think you can put V in and still get A times V in, save for a sign? Yeah. So, another alternate way of doing this is to say I am going to short this to ground even during phi Az bar and apply the input during phi Az. I am going to connect this to ground and during phi Az bar I am going to connect this to V in, and one immediate thing that comes to mind is that this node is connected to ground all the time. So, there is no need for these switches, you can connect this to ground all the time, and this will be, this voltage will therefore be V in V in minus V offset, right. Correct. And the output voltage will be V offset minus V in minus V offset minus V in minus V offset times A, which is A times minus V in. Is this clear? Okay. So, one obvious question that comes is, I mean, why would I want to do this? Is there any special reason for doing this rather than this? Any thoughts? Basically, the offset cancellation is the same in both cases. The only difference is where the input is applied, right. So, what topologically different thing do you notice here versus here?
This is non-inverting. This is inverting and delay inverting.
I mean, of course, it is inverting, but can you see a fundamental difference between the two? As far as offset cancellation is concerned, as far as estimating offset is concerned, in fact if I remove the input, correct. One crucial difference between both these schematics is that this node is always connected to ground in the latter case, whereas here that is not true. You understand? Okay. So it turns out then when we try and make this fully differential, why are we interested in making it fully differential? The flash ADD converter we are going to build will be something which compares a differential input against differential references. Do you understand what I am saying? The input, as we discussed a few classes back on an analog IC, on an analog mixed signal chip, it always makes sense for the input to be fully differential because a lot of common mode disturbances can be eliminated. Then the definition of a flash converter becomes, instead of comparing a single ended input with a single ended reference, a differential input is compared with a differential reference, which means that the latches which have to be differential, as we have already, we have already discussed differential latches, right. And it also means therefore that the input to the preamp is not going to be single ended, it is going to be differential. Okay. And it turns out, as I will discuss in the next class, that it is very straightforward to convert a single ended schematic like this, where the positive terminal of the amplifier is grounded to a differential circuit configuration than a schematic like this. All right. So the way this schematic is, the basic idea is drawn, can be redrawn in the following way. CAZ, this is phi AZ, this is phi AZ bar, sorry, this is phi AZ, this is V, this is ground, this is V in, this is phi AZ bar. This is just redrawing the old schematic in a slightly different way, but it is indeed the same thing. The gain is negative, so this is an inverting amplifier and the output voltage will be minus A times V. All right. So notice that this capacitor CAZ is basically acting like a battery which holds the offset. We also need to subtract references. So what do you suggest we could do? Please note that this is acting like a CAZ is simply acting like a battery which stores the offset. If you want to subtract a reference, in principle what you must do is connect in series with Vn another battery which stores the reference. Now the question is, hey, we already have one battery which stores the offset, can you use the same capacitor to also store the reference, correct? So any suggestions? Very good. So the observation is that hey, during the auto 0 phase, this plate of the capacitor is getting charged to minus V offset, okay, because what do you assume? Our offset was like this, correct. So, the observation is, instead of simply grounding this plate of the capacitor, if this was connected to some reference V ref, then the voltage across this capacitor will be V ref plus V offset, correct. So, this plate will be at V ref, the other plate will be at minus V offset. So, the effective voltage drop across the capacitor will be V ref plus V offset. So, the voltage at the negative terminal of the amplifier will be V in minus V ref minus plus V offset. This is the negative terminal of the amplifier. The positive terminal is at minus V ref minus V offset, and this is getting multiplied by A, and this will be minus A times V in minus V ref. Correct. So, the offset storage capacitor can also be used to store the reference, all right. Of course, one thing that none of you caught is that the output voltage will be equal to V offset. I mean, during the auto 0 phase, for instance, here this switch is shorted and this is grounded, this output is going to be minus V offset only if A is infinity. In practice, it is not quite infinity. So, the output voltage will be slightly smaller than minus V offset in magnitude, and so we will still be making an error in the, we are estimating V offset which is slightly in error. So, when you subtract also, we will be not compensating for the entire offset, but only a large part of it. So, in the next class we will see what the error is and how one goes and designs the preamp, and more importantly how one makes the preamp differential.